Good afternoon, ladies and gentlemen, and welcome to this workshop. We have ahead of us a session dedicated to swarm robotics, and definitely I don't think anybody, either in this room or online, needs a definition of swarm robotics. You're all specialists, but just in case anyway. Swarm robotics focuses on the development of large, scalable, and decentralized multi-robot teams. And these teams have the ability to move and carry out tasks collectively. And what used to be science fiction, what used to be a dream, is now a mature technology. And that technology produces extremely valuable applications. We are going to talk this afternoon about several projects, and all the projects we're going to talk about have been funded by the EIC Pathfinder. So this is the opportunity to learn more about the practical applications of swarm robotics, and to do so, we have 4 guests with us this afternoon. To my immediate right, Professor Peter Baltus, who's from the Technology University of Eindhoven in the Netherlands, and he's a professor in high-frequency electronics. Then we have Dr. Dirkjan Krijnders. He's from the Roboteer group, which is an engineering firm. We have also with us Dr. Vladimir Djapic, who's the CEO of H2O Robotics, and Professor Tomas Krajnik from the Czech Technical University in Prague, and he specializes in mobile robotics. So welcome to you all, gentlemen, and I will indeed, one after the other, invite you to present your projects and tell us what you have been working on. So, Peter, you will be first.
Thank you very much, Florence. And thank you also to Adelina Nicolai for inviting me to talk today about my favorite project, which is Phoenix. Phoenix was a Fed Open project, and the technology that we wanted to address in this project was a technology that would allow us to explore inaccessible environments. And that sounds rather abstract, but really there are a lot of practical problems and applications where we have these inaccessible environments. And let me give you a few examples. For example, you see in the upper right a chemical plant, and very often people that operate such a plant, they want to know what's going on inside of process tanks or inside of pipes, and they are not easily accessible. It could also be, for example, a nuclear reactor where there's been a failure and where you want to know what's going on without really wanting to go in there yourself. Closer to home, in your street where you live, there might be, or there very likely will be, pipes underground carrying drinking water, gas, waste water, and so on. And the companies that operate and maintain these pipes, they want to know whether these pipes are blocked, whether they're leaking. Sometimes they just want to know where they are. But there are more applications. For example, top right, we are sending rockets to far planets to find out what's going on there. And once you travel there, of course, you want to explore that environment. And close by again, if you're a doctor in a hospital, you can have patients, and you might wonder what's going on inside these patients without necessarily wanting to open them up to find out. So these are just a few examples. There are many more, but these are the class of applications, the class of problems that we wanted to address with Phoenix. And in Phoenix, we settled on a technology where we would insert a sensor into this inaccessible environment. That sensor would do observations. It would make recordings in its memory of a number of parameters. Eventually, we would retrieve that sensor, we would read out the memory, and we would have information about that inaccessible environment. Very basic idea, but then you have to make a choice. You can either go for a super sensor that is fully configurable, that's universal, that can do everything, really great sensor, with just one drawback, and that's that it's great physically. It has to be to do all these things. And that means it cannot necessarily go everywhere. It might be too big to fit. So what we decided in Phoenix was to go the other direction. Rather than make one super sensor, we make a whole swarm of limited sensors, small sensors, that each do part of the task and that together can do as much or more than a super sensor, but that are small enough to go everywhere. There's just one fundamental problem. When you make limited sensors, you have to make choices. You need to configure them. What to measure, where to measure, how precise to measure, how often to measure. And you need to optimize that for the environment that you're going to explore. But the problem is that you don't necessarily know that environment because it's an inaccessible environment. And if you knew everything, you wouldn't explore it. So we have this famous chicken and egg problem where you want to optimize the sensor for something that you don't know. And that's where the crazy idea came from that started Phoenix. What if we would make the sensors evolving, becoming better in hardware and in software over time, better and better adapted to explore this environment? And we solved that by making the sensors in a way that they can evolve, and then make a co-evolution where we evolved both the models of the environment and the sensors simultaneously through iterations both in simulation and in the real world. And in that way, we were able to observe inaccessible environments in an optimum way. Of course, to do that, it's a lot of work. And fortunately, we had a very good team. You see all the people here, and you see the different kinds of knowledge that you need to integrate. Software, user interfaces, mechanics, electronics, system design. And we were very fortunate, and I was very fortunate, to have the opportunity to work with such a brilliant team. The one person that's not visible there is Adelina, but she was indispensable through all the adventures of this project, and we were very, very fortunate to have her as a project officer. At the bottom, you also see the organizations that are involved in this. It really was quite an undertaking, but in the end, we got from this crazy idea to a technology demonstrator that showed that the basic technology works. And we verified that by having some PhD students, as you can see in the top right, top left, sorry, verify that in setups. And once you combine students with water and walls, then they can have a lot of fun and show that the things are working. And in the process, they also flooded our building twice, but we won't talk about it again. But then, when you have done that, and the project ends, then you find out that there's more that you would like to do, because the basic technology, generic technology works, but you would like to, on one hand, bring that technology from a technology demonstrator, from a concept, to something that can really be used in industrial settings. And for that, we are very fortunate that we had a follow-up project about which Dirkjan Krijnders from Antea, who's sitting here, will talk in the next presentation. And that will show you how we brought this concept into the real world. At the same time, we also see that there's new questions coming up from other applications that would like to use the same generic technology, but they have different boundary conditions. And for that, we would like to do more research, like, for example, evolving different physical shapes of sensors, or having smaller sensors even, or having sensors that can do more different ways of localization, and so on. So that's where we are now, and for that, we are currently also considering, in parallel to the industrialization, whether we should have a follow-up research project to evolve the technology to these specific applications. So I hope this gives you some idea of what we have been doing. I would like to thank you for your attention and give the floor back to Florence.
Thank you very much, Peter. Come back to your seat, and I have a quick question for you, actually. What is, in your view, the most prominent obstacle to seeing this kind of tech on the market?
I think it's the work that happens after you finish the research, after you've done the first steps towards industrializing it, towards the first application. then suddenly there's more people that think, ah, this is great, I can also use this, but they have slightly different requirements. It needs to be smaller, it needs to be more robust, it needs to withstand higher pressures, it needs to work in vacuum, whatever. And suddenly you have all these enthusiastic people with these great ideas, but all the people that you've worked with, this brilliant team, they're all gone. And then what do you do? How do you follow up on that?
Yeah, sort of making sure that the next step can be actually accomplished.
Exactly. Yeah.
Dirk, what about your project? I mean, we have, you know, Peter has touched upon it, but more concretely.
Yes, so I'm Dirkjan Krijnders. I work for a big engineering firm in the Netherlands, Roboteer Group. And we were one of the partners in the Phoenix project, and I was there involved in actually building the first prototypes. And as Peter already said, when you have this brilliant project, with actually some working prototype, student level, academic, hack together prototypes, where you definitely see some potential in the market, especially working for an engineering firm that has clients that have the problems that Peter mentioned. So we asked for what was known back then as a FAT launchpad, to find out the business model and to do to test the technology that was usable in the field. That was one side. And the other side is, can we make a feasible or a viable business out of that? That question turned out to be rather hard, but I'll get to there. The first thing we did was, well, take the prototypes that already worked for the students, and well, afterwards the people here can have a close look, but they're what you expect after a student project. And we took them to these mixing tanks. And that was really interesting because we could measure things in these tanks that were probably never measured before, because we come everywhere in these mixing tanks. And that was really valuable for, in this case, the manufacturer of the mixing apparatus that you see in the middle, because they have their simulations, they have their models, they have their experience, but they never really measured it. So this was one where we really started really started going. But one of the things here we found, for example, is these people need to know on which depth they are. So we needed to add a pressure sensor. And you can see the physical damage on the modes here. We need to have tough modes for this application. The second pilot that we were doing was going into big pipelines, big industrial pipelines. We had a very nice pilot set up at the drinking water company, and we wanted to do that pilot in March, and then Corona closed it, and of course we were not allowed. So that was a big setback. Here we're going into a sewage system, which was a little bit less sensitive to the public health, so these people still wanted us. And this shot is the last shot we ever saw of these modes, because we lost them. And one of the things that happens if you go into water, there's no radio communication, so we need to retrieve these modes to find, to get the information out of them. So actually, somewhere in the sewer in the south of the Netherlands, are still 10 of our modes. And for a starting project, that was quite a setback, because that were 10 out of the 12 of our prototypes. That was tough. And it showed us that we really need to work if we want to do anything in the pipeline business. And another thing that we learned in talking to other clients or to other potential clients is, for example, if you want to go into firewater mains, but those work at 30 bars. Well, 3 printed balls at 30 bars at this size is quite a challenge. So one other thing that we did during that time is we did work on the hardware. So what you can see is the migration literally from Phoenix to something that starts looking like a product also. I mean, there's not massive wires inside, everything is nice and clean. Thanks to Corona, it took quite a bit longer to create these, so these are actually a week old. But we're really hoping to now visit more and more clients because we can handle the pressures, we can handle the leakage because the student project leaked easier. But we hope that makes it a really viable business. And well, here you see lots of people looking very interesting at the test mixing tank. But this is going to be our first, probably the first commercial business, like really measuring in the mixing tanks and verifying that what they measure on the outside of the tank, that they can correlate that to what they're measuring inside. And the current plan is still to have that joint venture starting soon, but Corona makes things like that hard, and the component shortage makes that actually creating the hardware to support the business decisions is also hard sometimes. But this is really, this is likely to happen in the next few months, so it really helped us. And that was in short what I had to tell.
Thank you very much, Dirk. And what, to you, was the value added of the FET funding part of Pathfinder?
The value added was basically time. Time to figure out what do we have to do, what fields can we apply this in, and what do we have to still do to reach those fields. And that running these pilots really took a lot of time. Mm-hmm. And thanks to the Launchpad project, we had that time. We could really have 4 or 5 meetings with the client before we actually committed to doing a pilot, and we could really get the information out of there that we wanted. So I think that's really valuable for starting the correct company in a bit. Yeah.
Yeah, you didn't have the pressure of tight deadlines.
Exactly. There was really the time to explore and to find out, okay, we need to add a pressure sensor, and we need to have a second pilot to verify that now it gives the things that the client is really interested in. And that was really valuable because now we have the data to support the business decisions.
Yeah.
Yeah.
Very good. Vladimir, what happened on your side?
Okay, yeah. So just to touch on the previous presentation, so maybe we cannot help you find the ones that you lost, but maybe in future we can work together. So we add some of our technology to them so they don't get lost or they can be retrieved. We can know their position. So I'll talk about the H2 Robotics and our company that is came from basically Pathfinder FET project. One of them, another one, we actually developed new products based on the technology developed in the Pathfinder. Thank you, Adalina, for inviting me. So H2 Robotics is a company that is a spin-off from University of Zagreb, and you can see there 15 years of technology, and we come from automatic control department, and robotics in particular, robots that work in hard ocean environments is something that is our background. So robotic vehicles that work underwater, so they're used for different mapping missions underwater, as well as surface vehicles, autonomous surface vehicles that swim on the water surfaces and can do the job, but they can also provide a communication link with the swarm that is underwater and the rest of the world. So the next slide is that this particular surface vehicle, autonomous surface platform, is unique in its characteristics, and it is from the FP7 project that merged the robotic technology and humans. So in this case, the diving mission was identified as a particular mission where the robot can help the divers. So it can provide safety, so it can be above the diver at all times. It can provide a communication with the rest of the world, so an operator that is supporting the dive mission on the boat, and it can also provide the positioning. So any type of data that the diver that is doing the biology type of mission or archaeology, any type of data can be georeferenced. So the second project that is from Pathfinder, which is Subcultron projects, actually put this robot together with many small vehicles. So in addition to this muscles, which were basically buoyancy-driven robots, the ones that do not directly control horizontal position, but vertically can go up and down, they can sample the ocean. So this complex system was to have the surface vehicle retrieve these A muscles and also recharge them. As you can see on the right-hand side, it's a fairly complex system, and it's not something that is easy to build and commercialize. So we had to look at the particular technology for this type of, so which technology, subset of technology can we take and take it to the market? So one logical path was to use the surface vehicle that was built that can be used for different missions. And this is something that is the first product that we launch on the market. And with the medium success, we have these systems deployed in the field. Different companies are using them for mapping surveys with either sonar or a video camera. We do a 3D reconstructions of this data. It's in particular, these vehicles can work in very harsh environments, in the rivers, close to the, in the port, close to the ships. So this is something that is technology that made sense to us. This is something that was our comfort zone, a surface vehicle, a robot. But what we kind of did not think at first is this acoustic communication technology and ranging that can be very useful. We just heard that if their devices were equipped with some ranging devices that we built, they can be retrieved. Their position can be known. So what we have is the H2O Observe, which is acoustic communication and positioning device, and also that technology, but packaged differently, which is there called H2O Orologio, works with the dive watch, and the divers can do chat messaging underwater. So just for people that don't know, RF waves, the radio frequency waves, do not travel. So for instance, Bluetooth, you need to be 1 centimeter away to work underwater. But what the animals and what we use is sound to transmit messages. So our path was to build what we need to build and utilize the technology that is readily available, which is the smartwatches, smartphones, and put those two technologies together. Here in the middle, you see our device working with the tablet, and also on the bottom with the smartphone. So the challenge here and the way for us was to transfer our communication and localization algorithms and put them in this, on these readily available devices and run them as an app. So for instance, a diver can go with the wrist unit and it can use the different, scroll down to different messages and send a message to another diver, or to an operator that is on the boat and it's receiving this on the cell phone. And this works up to, tested in different environments, up to 1,000 meters, but you can send only small text-like messages up to 450 bits per second. So this is something that we have as a first market opportunity. This is the diving market. Diving market is something that people, it's like other outdoor activities, people like to go dive, they invest in these gadgets. So we believe that this is something that is going to be very important. In addition to this, a variant of this device that we have that does not work with or does not need a Garmin watch, but can listen to some chemical parameters, can actually alert a parent if their child is drowning. So that's something that is also a higher potential for this technology. From subculture to product, again, we had a swarm of these A mussels being deployed in the lagoon of Venice, but we saw that there is a way to build housings for these type of systems in a smart way, in an efficient, in a cost-effective way. So we are entering pollution monitoring market and water pollution monitoring market with this technology.
I'm going to have to ask you to conclude, I'm afraid, Vladimir.
Yes, this is my last slide. So big vision for us is underwater Internet of Underwater Things. Everyone is talking about underwater Internet of Things, and now we're expanding this to the underwater environment. And this concludes my talk.
Thank you. Thank you very much. So what actual barriers did you have to overcome when you wanted to launch the company in that particular field?
So for us, the biggest barrier was to go out of our comfort zone and actually accept that potentially new market opportunities can be in subset of technologies. So we do have 15 years of experience in marine robotics, but it was this decision to actually define that the diving industry could be a big opportunity for us, and to focus on a subset technology for underwater communication and localization was the challenge. Then after that, we were able to make a path of how to do the transition of our algorithms to work with the technology that is available, smart phones and smart watches, and be able to make a product out of it.
Thank you. So yeah, indeed, Dirk, maybe you two need to talk about your... so there we are. New partnerships will be born from this particular experience. So Tomas, looking forward to hearing from your end what happened.
Thank you for arranging this meeting. Thank you for introducing me. So nothing actually happened yet because I'm presenting a project that's in its very infancy. The project started only 3 weeks ago. So I will talk about the concepts and about the possible future of using the swarm technology to make impact on our lives. So actually, what we are witnessing right now is like an ongoing ecological decline. And the changes in the environment, the overexploitation of the farmland, urbanization, and the climate change, they actually make it very, very difficult for many species to keep up with the change. And so what we are observing is like an unprecedented loss of biodiversity in the nature. So this loss is only comparable to actually extinction of dinosaurs if you talk about the actual if you talk about the biodiversity decline. One of the species that are actually affected a lot are these flying insects. So over the last 20 years, there is a 75% decline of the flying insect mass, which actually is very convenient for drivers because you don't have to clean your windshield. However, this is a tremendous impact on the ecosystems because these insects provide a very important environmental service, and that's the pollination service. So if you have less of these, you actually have less crops. If you have less crops, you have less insects, and you are caught in this vicious cycle that actually might lead not to ecological decline, but to an actual disaster. And this is also an economical impact, because 84% of crop production in the EU actually directly depends on this pollination service. So out of these flying insects, the most prominent pollinator provider is the honeybee. So the honeybee actually pollinates most of the crops, and also there are some crops that are only served by honeybees themselves. And the honeybee population, similarly to the other flying insects, is also suffering from this population decline, and we have the invasive species that injure the colonies, we have the colony collapse disorder, etc., etc. So in our project, what we are trying to do is to introduce mobile robots inside of honeybee colonies in order to improve their health and to also to improve their efficiency in providing this pollination service. So in the past years, our colleagues were studying, the project partners were actually studying robots that are able to act in the environment for extended periods of time. And if you want your robot to act autonomously for a long time, the robot has to be able to adapt to the environment. So we came up with methods that allow the robots not only to adapt, but to understand what is the nature of the change of the environment, what is the overall environmental dynamics. And this allows deployment of robots in environments which are subject to, let's say, seasonal variations or day and night variations, but also this allows deployment of robots that interact with biological systems, like the ones here on the picture. So in this case, we have been deploying robots, for example, in hospitals, where they had to understand what is the long-term dynamics of human behavior and act in a way that they would blend in this environment. There is another project that's actually mentioned by Vladimir, and that's the subcultron. And again, in here, swarms were deployed in order to monitor the ecosystem in the Venice Lagoon. So in this project, in the RoboRoyal, we are making one step more, and we are not only going to observe and model and to forecast the environment changes, and not only to make the robot to understand the environment change, but what we are going to try is that we are going to use the robots to influence how the environment change happens. And to achieve that, what we will try to do,
Green.
I am pressing the green. Okay.
There we are.
Right. I think I'm not pressing anything. Okay. Anyway, so let me go back. So what we are going to do is that we are going to introduce mobile robots inside of beehives. And a beehive is a relatively complex system where you have this queen releasing chemicals, and these chemicals actually influence the overall activity of the colony, basically what the worker bees do. Then the worker bees go out in the environment, they interact with the surrounding ecosystem, and then when they go back, they interact with the queen, and the queen actually gets information from them about not only the colony itself, but also about the surrounding ecosystem around the colony. So based actually on the feedback from the worker bees, the queen is adjusting this pheromone mix that controls the colony activities in an informed way. The problem is that when you have changes that were never observed before by these species, the queen might actually not adjust this pheromone mix, these chemical substances, accordingly to react properly to the environment changes that are going around. And this actually decreases the ability of these colonies to cope up with the change. So in this project in particular, what we are trying to do is that we will introduce these robots in the beehives. They will observe for a long time what's going on around. Then we will build mathematical models that allow us to characterize the interactions inside of the beehive, between the queen, between the workers, and also the interactions of the beehive with the surrounding ecosystems. Then we will actually use these artificial agents to interact with the queen in a way that we provide her with the right information to adjust this pheromone mix that drives the activity of the beehive in a way that the beehive is actually more efficient. So we can basically increase the pollination when we need it. We can increase the gathering for the beehive in order to accelerate the brood. etc. So this is the overall idea of the project, is to act upon one of these important cornerstone species in order to improve the ecosystem stability. So what you have seen here in this presentation is this technology where we introduce robotic agents in order to affect the queen, to make her happy. And yeah, that concludes my speech. Thank you.
Thank you very much, Tomas. Thank you, and I invite you to go back to your seat. It's fascinating indeed, and I'm sure that in a couple of years, everybody will be very curious to have you come back here and tell us where you actually stand and how much progress you have made. But now that we've seen the birth of the project, what does it take, or what did it take to be funded by the EIC Pathfinder?
So I have to say that for a technologist, we are very passionate about these robots and these devices. So we want to make these devices very sophisticated. And what we would like to see in the grants that we deploy really, really super high-tech technology in order to achieve something. But I think to get the FET, one has to have in mind always the market value of the resulting systems, and also like the real societal impact. So sometimes you have to think maybe the same goals can be achieved with less complicated, less complex technology that's actually just deployed in a smarter way. And I think that that's one of the main things to keep in mind when you go for these FET projects.
Right. Do we have questions here in the room? Because we do have a few minutes to spare, and I promised we'd save some time for Q&As. No questions? I mean, such interesting experiences should trigger some curiosity. No? Do you gentlemen have a question for one another? I mean, or a reaction to somebody else's presentation or somebody else's project? I mean, we heard already that there may be some cooperation between two of you, but do you, I don't know, do you cooperate with other universities, other scientists, not necessarily in the development, but once you have reached the stages that you have already reached when your project's a little more advanced? Peter, maybe yeah. Yes.
Yeah. So maybe I have not had a chance yet to pre-discuss this with Tomas, but I would be interested to better understand how the adaptation in your case works. Right? Is that something that works also iteratively, or is that something that is more like a control loop mechanism?
So basically, these adaptive mechanisms that can cope with the environment change, these were actually mostly developed during FP7 Strands project that was especially aimed at spatio-temporal representations for long-term applications of mobile robots. And what we did in there is that, you know, in robotics, when you want to represent uncertainty and incomplete knowledge, you typically use traditional probability. And this probability is typically taken as a, you know, as a constant, and you treat it only, you update it only through observations. And what we tried there is to use alternative representations of this uncertainty over time, for example, spectral models or multidimensional models of time. And this actually allows to capture certain variations that are cyclic or that are governed by certain processes that we can get. So this adaptive technology is based on this algorithm that was called Freeman, Frequency Map Enhancement, that was actually developed in previous FET FP7 projects.
Do you think this might be used or might be applicable in Phoenix-like or Smarbles-like applications? Currently, we are exploring the environment as is, right? So we see how it is now, but you can imagine that for some of these applications, you probably want to regularly redo such inspections. And if you have pipelines, for example, and you find out that it's working now, except for one leak, maybe after a year you want to check again, see whether there are new leaks and so on. And probably what you're most interested in would be deltas, right? Changes.
I mean, exactly, because once you have a robotic system and you do your first round of exploration, then you already know everything about the environment structure. And this is like sort of state of the art in robotics. You build a structure and people are competing in how precise and how large maps they can actually build. And when they want robots operating inside of these structures, they neglect the change. They want to get rid of the change. However, if you do exploration for the second time, it is the change that you are interested in, because the change tells you not only how the environment looks like, but what is going on in there. So I definitely think that, you know, for industrial inspection, these deltas are not only important, they are crucial. This is what you want to know. And this technology I was talking about actually allows you to schedule your inspections in a smart way so that you actually maximize the probability to sense these deltas and to get the most information out of them.
Exactly. So that would allow, maybe if we could make that interact with the evolution, that could allow the evolution to be steered towards really focusing on the deltas rather than collecting lots of redundant data over time.
Yeah, exactly.
I think we need to have a cup of coffee afterwards.
Okay.
Dirk, I could see you nodding throughout this whole conversation. Is that, I mean, when Tomas was talking about the approach that they have followed, is that the approach that you followed as well?
It's one of the, I think one of the things that we need, because traditionally, as you said, you've tried to make a complete map, but one of the things we do is we sample, for example, very much information as soon as we hit a wall. So we get a sparse sampling of a pipeline, but it's very hard then to build a complete map. So I can see where there's yeah, the overlap is clear. Yeah.
Yeah. You too, Vladimir?
Oh yeah, definitely. Definitely like this, these technologies and subsets of technologies that we have developed can probably be, if we think a little bit more, put together in something larger.
Thank you. Do we have a final question in the room?
Yeah.
Yes, I can see somebody there.
I'm Natasha, working for the European Commission. I would just like, I mean, it's a brilliant technology, and I think all of your projects are very inspiring. Thanks for that. But for someone who comes from also business world before joining the Commission, I was just wondering, how is your path on going to the market, from research going actually to the market, and later on scaling up? Considering the incomplete single market we have in Europe, considering fragmentation, and considering the fact that we are very much, when it comes to risk financing, we are lagging behind our competitors, mostly US and China. So for me, it's more like, okay, going from a research phase, because it's great. I mean, I think especially what you were explaining, Dirk, it's very interesting. But like, how then we go to a market? How do we scale up? And how we, you know, how you create this more investment that goes beyond European funding, but then attracts also private investment as well.
Yeah, so to answer a couple of your questions, so the diverse market, we did not yet explore. We just stayed in the Netherlands so far. There's enough to do there. And this second thing, and but that has a background in where I work now, is we got the support from a big engineering firm almost by luck. But that also makes our finance model so far a little bit easier, because I have time to work on it while I have a job. And we start the business at the moment that we think, okay, now this can stand on its own, and we have partners that are strong enough to start this. But that is a way also of evading the risk that you mentioned. But I hope that we found a way to in a risk-evading way, still start the company soon. Yeah.
Vladimir, maybe you'd like to add something to this, because you've also been through that process.
I can add to something. Yeah, so basically the business model that we have now, because the technology is new, is to develop some units that will be loaned or given to dive centers for a tryout period of a month or half a month or something like that. So some type of program that can enable that. So the units are working now. We just need to build larger quantities to be able to insert them. They're not too expensive. I'm not talking about millions and millions of euros, but just to be able to have them ready and taken to different potential customers. If they see the value, they could keep them. So something like that can be a way to insert them, you know, in addition to trying to invest a lot into marketing and be able to sell online. A loaner program to buy something like that can be very useful for us, for instance.
Thank you. Peter, did you want to add something to this? Okay, I think we're going to wrap here, simply because we now have a final session to go to, and we're going to be closing our day. But before that, I'd like to thank our speakers. I think that now that the conversation was picking up, we could have continued for a while. So I'm delighted at least that you got to know one another and maybe saw some cooperation possibilities. Ladies and gentlemen, thank you very much for following us here in the room, but also online. And I wish you a nice rest of the day. Now I invite you back to the mezzanine for those of you who are here in the room for our closing session. Thank you. Bye-bye.